Good evening, dear colleagues. My name is Mamaeva Anastasia, and today I will present our work titled Optimize Pruning Strategies for Non-Local Architectures in Lung Computed Tomography Tumor Recognition. This work focused on making attention-augmented medical images models more efficient while preserving strong performance on two clinically relevant tasks: lung tumor classification and lesion segmentation. Deep learning models in medical images are becoming more accurate, but also more computationally expensive. This is especially important in lung CT analysis, where models often process high-resolution images and may need to provide more than one prediction, such as classification and segmentation, at the same time. In practical deployment, hospitals and clinical centers may not always have access to high-end hardware, and fast inference is important for screening, triage, and decision support. That is why model efficiency matters. In this work, we study pruning as a way to reduce computation, memory use, and latency without losing clinically meaningful quality. Unit-style encoder-decoder models are still a strong baseline for medical image segmentation. They work well because they combine information from different scales and keep information special details. At the same time, attention and non-local models can improve the model. They help it capture long-range dependencies and global context, which is useful for difficult lesion analysis in CT images. However, these improvements also make the model heavier. Attention and non-local operation increase flops, memory use, and latency. The main research gap is that standard pruning methods are usually made for more common model architectures. They don't always work well for attention-based encoder-decoder models, especially in multitask medical setting. Our goal is to create a more resource-efficient version of a specialized non-local unit for lung CT analysis. The main challenge is to compress the model while keeping good performance on both tasks at the same time. First, neoplasm present recognition, and second, lesion segmentation. This is difficult because not all parts of the network are equally important. Some lesion and models are much more sensitive than others, so simple pruning can hurt their quality too much. The baseline model in this work is an attention-augmented unit with specialized non-local blocks. It's designed for joint analysis of single-channel CT images and gives both classification and segmentation outputs. In general, pruning means removing parameters or structure parts of the network under sparsity constraints, while trying to keep the loss as low as possible. We compare several pruning approaches. First, global magnitude pruning, which is unstructured and removes weights with small magnitude. Second, structured channel pruning, which is more suitable for real hardware. Third, attention head pruning, which focuses on the attention part of the model. And finally, our proposed sensitive aware pruning strategy, which is designed specially for this architecture. Our main contribution is a customized pruning strategy designed specially for this lung CT pipeline. The first part is sensitive aware layer-wise sparsity allocation. Instead of pruning all layers in the same way, we estimate how sensitive each layer is. Then we apply less pruning to the most important parts of the network. The second part is activation norm-guided importance scoring. This helps us find units that really contribute to the useful feature representation, especially in diagnostic important foreground regions. The third part is background suppressions in later space. Lung CT images often contain large background areas that don't have much diagnostic value. So we try to reduce unnecessary computation in those regions. Together, this idea helps us remove redundant computation while keeping the most important task-related capacity of the model. To evaluate the methods, we built a joint benchmark from several public lung CT dataset and an additional subset from Radiology Moscow and TCAI. This creates a more realistic setting because the data come from different sources. For classification, we report precision, recall, and F1 score. For segmentation, we report mean, intersection over union, and dice coefficient. To measure efficiency, we also compare the number of parameters, flops, and inference latency on the same hardware setup. So, our evaluation shows both medical quality and computational efficiency. The main result is that different pruning methods don't give the same practical benefit. For example, unstructured global magnitude pruning can greatly reduce the number of parameters, but it doesn't give a strong improvement in real inference spread. The baseline latency is 41.5 milliseconds, and with 50% GMP, it only decreases slightly to 40.6 milliseconds. This happens because unstructured sparsity is not very hardware-friendly. Structured pruning methods work better in practice, but the drop in quality becomes clear when sparsity becomes higher. Our proposed methods give the best overall balance between quality and efficiency. At 50% sparsity, it reached an F1 score of 0.923 MIOO of 0.742 and DICE of 0.846, while reducing latency to 23.6 milliseconds and flops to 30.8 gigaflops. At 60% sparsity, the method is still stable. It keeps F1 at 0.904 and MIO at 0.724, while reducing latency further to 19.4 milliseconds and flops to 23.5 gigaflops. So, the key takeaway is that architecture-aware pruning, preserving accuracy much better than generic pruning, while also giving strong deployment benefits. In conclusion, we showed that pruning can make attention-based lung CT models much more suitable for real deployment, but only if the pruning strategy matches the architecture. Our sensitively aware methods gives a better balance between predictive quality and computation efficiency than standard baselines. This makes the methods promising for practical medical AI systems. In the future work, we plan to test it on more CT datasets and combine it with other model compression and deployment techniques. Thank you for your attention. We appreciate your time and interest in our research. If you have any questions or would like to discuss further, please feel free to ask, open to your feedback and eager to engage in a productive discussion. Thank you.